I'm Dr. Joshua Reichert, Associate Faculty in the Forbes School of Business and Technology at Ashford University, and this is the Week 1 overview for CPT 301, Computer Organization and Architecture. This week you're working towards 2 learning outcomes. You will outline computer abstractions and technology and explain computer instructions. This week your assigned reading is 2 chapters in our textbook, Computer Organization and Design by Patterson and Hennessy. You'll be reading Chapter 1, Computer Abstractions and Technology, and Chapter 2, Instructions, Language of the Computer. I wanted to provide you some background information as a review if you've already had this, or perhaps as an introduction if you've not studied some of these concepts already in your prior coursework. Before we can get into computer organization and architecture and how computers process instructions, we need to start from the beginning with the fundamental language of the computer, which is binary numbers. Ultimately, binary is just a series of on and off signals. This is just electricity being turned on and off. It's literally electrons moving through wires or through silicon in the case of processor. But that's all it is an on-off switch, the same kind of switch essentially that you use to turn your lights on and off. The computer is simply pulsing this information very, very fast, but it's the same idea. Electricity is being turned on and electricity is being turned off. Binary numbers are the best way for computers to process information because we only have 2 states, a 1 or a 0, an on or an off. The easiest place to start with binary is to look at an 8-bit number. This is a number with effectively 8 binary digits. So on the top bar on this slide, you'll see a series of 1s and 0s. And each 1 and 0 being read from the right to the left represents 2 to a particular power. So if we look at the second row, this is showing the number 2 in decimal. That's the number system that most of us are used to, raised to a particular power. So the rightmost digit, which is a 1, meaning it's turned on, is 2 to the 0 power. 2 to the 0 power is decimal 1. The next digit to the left is a 0, meaning this particular digit is off. If it were on, it would represent 2 raised to the first power. The next digit to the left is 2 raised to the second power, and this one happens to be on. So 2 to the second power in decimal is 4. And so on and so forth. It goes all the way to 2 to the 7th power, which is 128. Effectively, all we do when we read a binary number is we check the place value of each binary digit, beginning from the right and working to the left, raise that particular digit to a particular power based on its place value, beginning with the number 2, so 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, 2 to the sixth power, 2 to the 7th power, and then we simply add together the digits that are turned on. So in the case of this number, the rightmost digit, 2 to the 0 power, is turned on. So we have a 1. The next digit to the left, 2 to the first power, is off, so we ignore that. The next digit to the left, 2 to the second power, is on, so we compute that. That's 4, 2 to the second power, 4, and we add that to the 1 from the rightmost digit. And we move to the left, 2 to the third power is off, so we don't count that. 2 to the fourth power is on, that's 16, so we add that. And 2 to the fifth power is on, that's 32, so we add that. And 2 to the sixth power and 2 to the 7th power are off. We now have our on digits, and we simply add them together. So 1 plus 4 plus 16 plus 32 equals 53. So if we look at this number in binary, we have, beginning at the right, 10101100. This is 53 in decimal. We could read it left to right, 0011, 01, 01, 53 in decimal. So it's essential that we understand how binary works, because without binary numbers, we would have no computers. Computers utterly depend on these on-off pulses in order to do anything. And every number, every computation, every instruction in our computer is ultimately reduced down to binary pulses, on-off pulses. So I wanted to provide this brief review of how binary works so that we can lay a foundation for everything else we'll be discussing this week and throughout our course. From binary numbers, we can begin to build what are called logic gates. Logic gates are the fundamental electrical components of a computer, in particular, the central processing unit itself, and more fundamentally, the arithmetic and logic unit, and what are called adders within that unit. These logic gates are based on Boolean algebra. Boolean algebra is a form of mathematics that was invented by Charles Boole that allowed us to do calculations and comparisons using nothing but true and false statements. Well, true and false is just like an on and off switch. So this became almost natural to use Boolean logic to create the first computers. So at the very foundation of our computers are these logic gates, and we'll talk about the electrical components that make this possible in just a moment. Before we do that, let's talk about how these binary numbers work together through these logic gates to allow the computer to make comparisons and ultimately to do addition, subtraction, multiplication, and division. So let's look at first the AND gate and the OR gate. This is the blue and pink diagram in the illustration. And below it, you'll see a truth table. So in the case of an AND gate, there are two inputs, A and B, and one output, F. If A and B are both off, the output will be off. If A and B are both on, the output will be on. But if either A or B are on or off, the output will always be off. So in other words, if both inputs are true, the output will be true. If both inputs are false, the output will be false. If either input is true or false, the output will always be false. An OR gate allows us to have a little more flexibility. So if both inputs are off, the output will be off. But if either of the two inputs are on, the output will be on. So we could say this is a comparison of OR. And of course, if both inputs are on, the output will be on. So the AND and OR gate are the fundamental logical components of any computer, and we extend those to other gates like the XOR gate, the NAND gate, the NOR gate, and the XNOR gate to give us a little more sophistication and to allow us to more rapidly build components like the adder, which allows the arithmetic and logic unit to conduct arithmetic. So at the very foundation of your computer are these on and off pulses, these binary signals, binary information, and these logic gates which process that information one bit at a time, one signal at a time. And ultimately from these logic gates we get what's called an adder. An adder allows us to do binary arithmetic, binary adding, and from binary adding we can do binary subtracting. And from adding and subtracting, we can then do multiplication and division, because multiplication is just repeated addition and division is just repeated subtraction. So once we have those fundamental components, we can start to abstract further and further and further out to build more and more sophisticated computations. And that's essentially what's happening behind the scenes in your computer. A very early electrical engineer and computer scientist, Claude Shannon, was the first to come up with the idea of using electrical relays and switching circuits to model Boolean algebra. And without his original work, we would not have our modern computers today. So he took Boolean algebra, Boolean logic, and took this abstract theoretical concept and applied it in the real world with electrical circuits. So we can thank Claude Shannon for his work of making binary logic and ultimately computation possible in the real world. Early computers used first what were called electrical relays, and that's the image in the center here. An electrical relay is a magnetic coil that essentially allows for switching on and off. So when you apply a charge to that coil, the magnet activates and it closes the electrical circuit, and when there's not a charge applied to it, the circuit is open. We still use electromechanical relays today. You can find them even in your automobile, in the electrical panel of your automobile, along with your fuses. You'll find electromechanical relays. In the early days of computers, there was also use of vacuum tubes, and vacuum tubes allowed state to be stored on and off in a very closed chamber, so you could move electrons in two directions within that vacuumed space inside of a glass tube. The problem with vacuum tubes was that they were very unreliable and they would burn out. So in the early computers, there are stories of people, in particular women, who worked these machines, who would spend the whole day just switching out vacuum tubes as they burned out and the computer was doing its computations. The problem with the electromechanical relay was that there were mechanical components. So anytime there's friction, ultimately those components are going to fail. It wasn't until the invention of the transistor, which you'll see in the far right image, that we finally had something reliable enough to create the kind of computers we know and love today. The transistor is what's called a solid state electronic component, and it's called a solid state component because there are no mechanical or moving parts in it. So it makes it very reliable, and essentially what's happening is you have what's called a semiconductor inside of that transistor, which in most cases is silicon, a silicon wafer, and we are controlling the flow of electrons between two sides of this semiconductor. It's called a semiconductor because sometimes it can act like a conductor and sometimes it can act like an insulator. So we can move these electrons back and forth. A transistor has three legs on it, as you can see in this image, and these are called the emitter, the base, and the collector. And effectively what you can do is send a small electrical pulse to the transistor, which tells it to turn on the flow of the circuit between the other two legs, and you now have an electrically controlled on and off switch, which makes creating these logic gates possible. So the transistor has really made the miniaturization of logic gates and ultimately what we now know of as computer processors possible in the modern world. Today, most computer processors are almost unfathomable. In fact, many of them are computer generated these days, so they're not even engineered by hand by human beings. It takes large amounts of computation just to design and ultimately manufacture the processors that we use today, and the transistors are effectively etched into silicon at such a microscopic level. We certainly cannot see them with the naked eye, and in many cases you need to have a very powerful microscope to even see the pathways that are etched into these silicon wafers. So it's really quite extraordinary how far the technology has come in such a short period of time. But the kind of transistors that we can use in homemade electronic circuits are readily available, and you can buy those and experiment with them, and you can even create rudimentary logic gates for yourself. Certainly the and or not gates are very easy to create with small transistors by yourself. So it's a great experiment that you could do to see exactly how these logic gates work. But our modern processors are almost unfathomably complex. and it allows us to do the kinds of things that we enjoy, like having a very powerful computer in our pocket with our smartphones. Now that we've covered the fundamental components of the processor, I want to talk about some of the larger components that you might find on a computer motherboard. So here's the image of a pretty standard PC motherboard. In fact, I think you can even see the Dell logo on there. And what we see on this diagram are sockets for our memory, often called RAM, random access memory. We see a socket for our central processing unit, or CPU, and there are pins that fit down into that socket so that the rest of the motherboard can interface with the processor and vice versa. You'll see PCI slots, which allow for expansion cards. You'll see a backup battery, often called a CMOS battery. You'll see lots of other small integrated circuit chips all throughout this motherboard. And you'll see connectors for input-output, including your keyboard, your mouse, and your monitor or display. And this particular motherboard, which most modern motherboards now have, you'll also see a integrated graphics card or graphics processor embedded right on the motherboard. So our modern computers require quite sophisticated graphics processing, and there's many times a dedicated processor just for that. But the fundamental components that you see here is the central processing unit, memory slots, and input-output. One of the most helpful tools I have found for teaching computer architecture is a tool that was sent to schools back in the late 1960s called the Cardiac, the Cardboard Instructional Aid for Computing. And this was back in the day when schools simply did not have computers. It was almost science fiction to think that there could be computers in schools. The only people that had access to computers were the government and very large corporations, because computers effectively filled rooms, and it was impossible for ordinary people to get access to them. But the folks at Bell Laboratories recognized that school children, and high school students in particular, needed to be exposed to the theoretical or abstract concepts of how computers work. So they created a cardboard computer that they sent to schools. I happen to have about 10 or 12 of these in my own private collection, still in their envelopes, and in the original box that was shipped to a school in 1969 from Bell Labs. So it's one of my favorite components of my own private computer collection. But the Cardiac was actually a very helpful instructional aid to show just how the fundamental mechanics of any computer actually operates. So what would happen is you would control memory locations and instruction registers, which we'll talk about in a moment, with these little pull tabs, and then you would actually store values by writing them with a pencil over to the right in memory cells. And you would be able to construct a program with operational codes and input-output, store them in memory, and then manually watch the cardboard computer, so to speak, process the commands that you fed into it. And of course, you had to do all of this manually. So you would advance what's called the program counter. We'll talk about that in a moment as well. And then you would move this little ladybug, if you can see it in the illustration, into each memory cell as the program counter advanced and the computer did its computation. If this seems silly, I would encourage you to give it a second thought, because I find this to be very, very helpful. And sometimes, especially today, these things are so complicated, it's difficult for us to wrap our minds around them. But if we go back to some of these very simple fundamentals, it gives us a secure foundation for understanding how computers work in the modern world. So this is a very simple diagram of how the Cardiac paper computer was organized. There was input and output, which in that case was manual, literally with a pencil and paper. And you would feed input into the Cardiac by writing into memory cells. And there was an abstract control unit which would handle where in memory that information was stored. And you would advance the cell selector along with what's called the program counter, as you can see down below, by moving the ladybug into various slots as the computer ran. The program counter is effectively advancing memory locations as it reads instructions and values out of memory. So think of the program counter as a clock, and in fact all computers do have clocks. They have a crystal that oscillates and controls the speed at which the processor is running. So when we talk about how fast a computer is, so for example, a 1.5 or 2 gigahertz computer, we're talking about the speed at which a crystal is oscillating inside that computer and causing the electrons to flow through the silicon processor itself. So the program counter is keeping track of that. It's keeping track of effectively how many clock ticks have gone by, and it's advancing through memory as the program runs. So the program counter is running, the ladybug is moving down through the memory locations. As the ladybug moves down the memory locations, the control unit is reading both an opcode and an address. An opcode is an operational code that the computer fundamentally understands in machine language. So every processor has them. And processors have what are called instruction sets, and each processor is different. So an Intel processor has a different instruction set than a Motorola processor or a RISC processor, and those are designed by the manufacturers. So any code that we write in higher level languages or even assembly ultimately has to be compiled down to machine language that the computer can understand. Those programs are stored as binary values in memory, and each memory location has a value as well. So there'll be an opcode and an address in each memory address, and as the program runs, the program counter advances according to the opcode that's provided and any operands that are provided along with it, and it works through the course of the program, and effectively the processor executes those things in different logic operations happen within the processor itself. The data in memory are modified, and ultimately that results in the input-output that we see when we interact with the computer. I'll mention just two things also on this diagram. You'll see what's called an accumulator and instruction registers. Registers are used as temporary storage locations within the processor itself, so you can store information for quick access as you're executing a program, so you don't have to go all the way out to memory to fetch that information. And the accumulator is a place where a lot of the mathematical operations will be stored temporarily, so you can do computations, store it in the accumulator, and then move it to another location in memory. And we're going to talk about that in a moment when we look at some sample assembly code. Ultimately, this is a diagram of what every computer processor looks like. You'll see the central processing unit contains an ALU, an accumulator, control unit, and instruction decoder. So each instruction's coming through, it needs to know what that instruction means and what to do with it. There are instruction registers, data registers, which interface with memory, and the program counter is interfacing with the clock and with memory locations to keep track of where the program is as it's executing. And of course, there are input and output buffers that interact with memory so that what's in memory can ultimately come back to us to use in a meaningful way. So it may go to our monitor, it may go to our sound card, it may receive input from our keyboard or our mouse or some other device. But ultimately, all of that gets translated into binary, comes back to the computer, has some sort of opcode that tells the processor what to do with it, and then that's processed and information is fed back to memory, and we get feedback as output from the computer itself. So any computer, any processor operates on these fundamental principles. I mentioned this earlier, but it's worth repeating. All of the code that we are used to writing as programmers these days in things like Java and C# and C++ is ultimately compiled into machine code so that processors can understand it. In the case of Java, it's a little different because Java is actually compiled into bytecode that runs in a Java virtual machine, which can run on any computer architecture. But in the case of a C# or C++ application, for example, you may compile that to run as a Windows application, which generally is going to run on an Intel architecture, an x86 or 64-bit architecture. And it has to translate the code that you wrote into machine code that the Intel processor can understand. Processors can only understand the commands or the opcodes that were designed into them by their engineers. So processors do not understand C++, they do not understand Java, they do not understand, certainly not things like Python or JavaScript, which are interpreted languages. Ultimately, all they understand is machine code, which are commands that are engineered into the chip using those logic gates that we looked at earlier. Now, assembly language is a low-level language that's a bit closer to machine code, but it's human readable. And you have to understand that in the early days of computing, this was a luxury. So programmers were not putting in memory locations one at a time in binary. They could actually use some level of abstraction to write code, and this was a great luxury to them. It looks perhaps daunting to us today, but compared to putting in binary codes one at a time, this is a much better alternative. But it does map almost directly to the operational codes that the processor recognizes. And so compilers ultimately compile these assembly code into machine code so that the processor can understand it. The high-level languages conceivably could move from architecture to architecture as long as you had an assembler and then a compiler that could take that code and translate it into machine code for a particular processor's architecture. I'd like to provide you with a very simple example of how a computer may process assembly language commands one by one. In this example, you'll see 400 through 412, which represent memory cell locations. So at memory location 400, we have the opcode move, and then we have two operands, 301 and 302. At memory location 404, we have the opcode add and two operands, 301 and 302, and so on and so forth. Over to the right, you'll see memory locations 301 and 302 because those are the memory locations we'll be manipulating, and then memory location 500 over to the right. We're going to assume that memory location 500 is mapped to a particular location on the output or the display, and this is often the case that particular memory locations are memory mapped to input-output within the computer's architecture. So what we're going to do in this example is effectively add two numbers together and then display that number on the screen. And this gives you a sense of what's happening behind the scenes. Now remember, this is another layer of abstraction above machine code. So this is assembly language. If this were in machine code, these would all be binary values, including the memory locations themselves. I'd put them in decimal just for ease of use. So imagine all of these values, and each opcode is going to be a binary value as well, representing that opcode. And then each operand would be a binary value as well, representing a memory location. So imagine all of these being binary. That's really what you're working with in machine code. So let's start at memory location 400. We have the opcode move, and we're going to move whatever is in memory location 301 to memory location 302. So when that happens, memory location 302 then becomes 005, which is the value that's stored in memory location 301. So that's decimal 5. Then we're going to move to, the program counter is keeping track of this, by the way. So the program counter is going to advance us now to memory location 404. And that's because 400 is the move command, 402 is 301 operand, and 403 is the operand 302, 404 is our next command, our opcode add. So now we're going to add the values in memory locations 301 and memory location 302. Now, oftentimes what will happen is when we do arithmetic like this, it's stored in what's called the accumulator. So down here in the right, you'll see a location for the accumulator. Once we execute the opcode add with these two operands, memory location 301 and 302, we add them together and we end up with decimal value 10 in the accumulator. The next opcode at location 407 is jump. This is an unconditional jump, which means that we're just going to advance to a different location in memory. So in this case, we're going to jump to memory location 410. It's down here. We're going to skip the halt command, which would stop the program from running. I'm going to jump to memory location 410, and this is an imaginary opcode store, which is going to take the value that's in the accumulator and move it to memory location 500. So here we go. Now the value 10 is in memory location 500, and we're going to halt the program. And because memory location 500 is mapped to input-output, we end up seeing the decimal value 10 displayed on our screen. Now this is all hypothetical, but it does give you a sense of what's happening behind the scenes when your computer is processing these opcodes and operands and interfacing at the processor's level to do simple addition or maybe to manipulate input and output. I hope you found this helpful. As you work through this week's assignments, please feel free to contact me via the Canvas inbox. I'm here to help, and I'll do everything I can to make you successful in this course. Have a great week.